pleasure to welcome Professor Alexander Heger from Monash University in Melbourne. Alex is a well-known international expert on stellar evolution, stellar explosions, nucleosynthesis, elementary yields from very massive stars. He has done his diploma in Munich at the Technical University a few years before me. Then he went to the MPA to get his PhD, working with Norbert Langer. Then he went to Santa Cruz, where we met again. He worked there with Stanford Brusley. And then he went on a Fermi Fellowship in 2003 to Chicago to work with Don Lamb and Jim Thorell. And then he became staff at Los Alamos, continued at explosions, or a site that is known for all kinds of explosions. Maybe it was too military-like, so he moved on to more moderate climates. He went to Minneapolis, to the University of Minnesota, where he left again in 2012 to down under to become full professor at Monash University, next to kangaroos and interesting other creatures. Since the start of this year, he is the director of the Monash Center for Astrophysics, which is part of the School of Physics and Astronomy at Monash Center. So let us welcome Alex, and let's hear a great talk about the life and death of the first stars.
Well, thank you very much for the introduction, and it's a great honor for me being invited to give you a Colloquium today on the life and death of the first stars. So what I've shown you is a movie that was one of the first simulations ever being done on the formation of the first stars by Tom Arnold and Mike Norman. And so I'll just show you this as a kind of historical document. And if you watch it now twice, I think I'm not going to go back another time because it takes so long in second big breaks by talk when I switch back apparently. And so at the end I put in the supernovae, so they studied this formation of the first stars from the primordial fluctuation. What you saw in the movie, you can try it, I can switch back, no it doesn't like it. We have to interrupt this, watch it one more time, but it takes its time to run. So what they started with is early fluctuations. What you see here is these isocontour surfaces. This is surfaces of equal density, and so you start here from some primordial clouds in the dark matter halo, and see formation of places of higher and higher density in this region from cooling as the gas falls in these dark matter halos. I think it's still a very pretty movie. It's not very high resolution as it appears, but now actually at some point the movie stops and they have a zoom in what happens there. And you can zoom in many levels of refinement towards the central object. And this is what we see as we go in. And I think this is still more or less the theme of many of the simulations that are being done today, except that at that time you will see in the very center some kind of small objects, and they had to stop when they formed here a clump in here of about 0.1 solar masses, because that started to get optically thick, and at the time they didn't have the radiation transfer to really deal with what happens in that case. And what they did instead is, what you will see, they artificially put in a supernovae. At the time they were also not able to really put the radiation feedback in from the star evolving and ionizing the halo around many things that people are doing now, especially around group. And so they put in a supernovae in the metals, and they then looked at how all of this looks like for the sake of having a nice visualization at the time. I think the scientific output from the supernova was not really great. Somehow this here all here we go. Okay. So what I want to talk today about is life and death of the first stars. So first, once we make these stars, how do they evolve? And in particular, two tool that we will be using is the abundance pattern nucleosynthesis that these stars make. And so much of the presented today has been done with 20 collaborators, Stan Woosley, Ken Chandler from a student who was first an IU Cooper Fellow and is now has the equivalent of a Hubble Fellowship but in the Asian Pacific region. Undergraduate student Conrad Chan, a student at Silver, Minnesota, Canada Hole, and also some work with Reagan, who's here. So we'll talk a little bit about the first stars, and then the tool that I want to use to understand what's going on with these stars, stellar forensics, and we'll talk about massive stars, possibly multiple stars, and very massive stars where I have probably, I might not get to this before you all are baked to death. Okay, so a brief history of the universe. There's actually two tales that one can think about. The first is the tale of light, and so we start with the cosmic dark ages after recombination, some maybe 300,000 years after the Big Bang, and this is a nice slide that I personally made from scratch. And then we get to the movie that you have seen, so the formation of the first stars and possibly the first supernovae that comes out. And then we end up in a universe that we see today that is filled with galaxies, 100 billion galaxies, and each of these galaxies consists of 100 billion stars. So it's a universe filled of stars. So it's quite some transition from nothing there to making some individual first stars to making one of these galaxies that now fill our universe. So it's quite some change. The second approach that you can have for this is the history of what the universe actually made of nucleosynthesis, of the elemental abundances. So what this figure shows here is the mass number of isotopes, and this shows the mass fraction of isotopes on a logarithmic scale. And so each of these dots is one isotope, and the lines, the same color, they connect the elements. And so you see, okay, it's essentially, since the logarithmic scale, essentially goes all hydrogen and helium, with some traces of lithium and possibly some other small traces of heavy elements, but really nothing sitting out here. And it's a big contrast to the nucleosynthesis picture of the universe that we get today, which is a universe filled with all of these elements in there, and all of these isotopes that are made in some way. And there's a lot of physics actually behind that, why the abundance pattern looks in this specific way, and there's contributions come from nuclear physics, from nuclear structure that you have to know, but on the other hand also from the sites where these things are being made that leave their imprint on why things are where they are. So it's both in the nature and how these, for example, supernova explosions work, how stars operate, that's kind of along with the underlying nuclear physics. So if your summary, so if this is the history of time, so we go from the dark ages, the first stars, the galaxies, and we go from the Big Bang abundances or abundance patterns being made by the first stars, and some of those we might still be able to trace today, to the solar abundance pattern. So first, a little bit about stellar evolution, in particular first stars. So what is very different from the first generation of stars is, from in contrast to stars that we see today, is that there were no metals present. So today stars form in molecular clouds, and as the name already says, there's molecules in there, so we have a complex chemistry, lots of dust there, but all of this is not present if the universe only consists of hydrogen and helium. The only molecules that we realistically make dominantly are hydrogen molecules. And so you can't get any cooling from metals. I assume you're all astronomers and know that metals, everything that's heavier than hydrogen and helium. Why does this play a role? If you look at the molecular cloud around with all of these metals in there, these things are very cold at about 10 Kelvin temperature. And in contrast to that, in the early universe with the first stars, you can't cool, and therefore you have much hotter clouds, and therefore you have the cloud has to be much bigger before it can collapse under its own gravity. And typically, today, typical mass scales of stars are around a solar mass, but when you go back in the early universe, and with these much higher temperatures, you estimate when your cloud collapses may have maybe around 1,000 solar masses, and then as a good astronomer, you take the thumb and estimate, well, maybe about 10% of that goes to the star, and then you make stars around 100 solar masses. Maybe some variation, 10 to 300 solar masses is a back of the envelope estimate. for a long time, and this was also a simulation that I had shown you for about a decade after the simulation, people believe you have this big monolithic clouds that collapse, making a star, and you will always make one big star in the center of this cloud, and there was not going to be any fragmentation. And this is what the simulations made us believe for that long time, and was kind of the paradigm. But only with the newer simulations that came out around 2010, people were able to resolve this, these very small scales. And yes, there was fragmentation, the same way as it is at present day, and so possibly you can make multiple stars as well. But the problem is, of course, that we don't have yet any direct observation of these stars, and will not have that for some time. And as you all know, that theory by itself, without being actually constrained observation, has not any value by itself. And so this is just kind of speculations, maybe educated speculations, but you really need to know better than that by having observational constraints. That's a nice picture from Heidelberg. We see one of some of the fluctuation binary stars. I think it's from some of the simulation, it's not really clear whether the star will separate it, but at some point will merge together. But people are making great progress in simulating this formation of the first stars and where this gets us. Here's another case of simulation where people try to simulate in the bigger domain various first generation of stars, so there's all stars made of primordial composition. They find also a big set of very big stars that can form. But the big question is, how do we really know, can we be sure that the first generation of stars were really big? And I found on the net some evidence, and I'll try to see if we can make this work. It's supposed to work. So this is, maybe some of you know, this is Google Sky, so you can go there at sky.google.com, and what we now try to do, so this is some nice nebula that you have seen before, and now let's try if we can click here, hopefully, and then you can zoom out. So just make this picture as the starting point, and in Google you can zoom out a lot until you see essentially the entire universe. So you see the galaxy here on our sky, and then you see the universe here from edge to edge. So right, this is also something that Google shows us. The universe has clearly an edge, and the edge corresponds, as we will look back, to the beginning of the universe. So the question, of course, is, okay, let's look at this. Let's look at what's at the edge of the universe at its very beginning. So let's zoom in there. And when you do this, so if you go a little bit in here, you see all of these stars. And if you go out towards the edge, you suddenly see there's very big stars there. So, so it's very clearly that at the edge, we know from Google that there's these very massive, very big stars sitting there. This one should be. Okay, so we have the proof. It's on Google Sky. So this is a done point that there's very big stars at the beginning of the universe. At least this is what Google tells us today. And you can search for it yourself, so it's not something I'm making up. But nevertheless, we can of course also wonder whether is it actually realistic that we can have such big stars. And there has been lots of discussion in literature whether you can make these big stars, and when they're metal rich, can you still have such big stars? And yes, we do find them in our own galaxies. So this is in the star in R136. There's some of these objects, and this object A1, people estimate has about 200 solar masses, initial mass. Another case that we know is Eta Carina. This is a star that has about 120 solar masses today. I think initially it must have had something like around 100 50 solar masses. So we can still make these big stars today. So why would it not be possible to make them in the early universe as well? And maybe they were dominant population back then. Another very interesting thing that Carina shows is that these lobes that you see around is actually not the star itself, the star sitting in here. This was some kind of mass ejection that came out of Eta Carina some 100 years ago, and it contains something of the order of 5 to 25 solar masses. So at some point, it was ejected in a few years. So at some point, the star had just decided, Eta Carina had decided, okay, I'm going to throw out 5 to 25 solar masses within a few years. And we don't understand the physics behind this, but it's apparently what some of these very massive stars are doing. But we don't know what's the physical mechanism behind it, and so we of course have to wonder in how far would this also be true for the first generation of stars. Does the same mechanism work there to give them these big mass ejections or not? But we don't know because we don't understand what's going on in these stars. And for stars that we cannot observe, it's not pretty much harder to tell whether this will happen there or not. Okay. So a very brief introduction to evolution of massive stars. I'll try to give you next. So we have this picture, we have a big gas cloud, and the gas cloud is cooling, is contracting, getting to higher and higher central density. And it actually turns out that this picture continues as the star evolves. So we see here central density and central temperature, and this is the typical evolution pattern of a star. We showed for a 15 and for a 25 solar mass star, and it continues through its life, contracting to ever higher central temperatures and central densities until it reaches some point up here, and then it will actually collapse and get even denser. So despite this general picture, this star actually doesn't just continuously contract, but it stops at some points here. That are indicated with nuclear burning phases, so it will stop here doing hydrogen burning, and it spends actually 90% of its lifetime here, and then it spends almost all of the rest of its lifetime somewhere around here, and then it just goes a little further, and then the last stages go increasingly fast. I actually have some table where I can show you some numbers, estimates for 20 solar mass star and a very big star, 200 solar mass star. So we have all of these burning stages that most of you will be familiar with. People first hydrogen, helium to carbon, oxygen, which goes about 10 times faster. Then we burn carbon to neon magnesium, which goes a lot faster. Then we burn neon to magnesium, and then timescales accelerate quite a bit. So the last burning stage is burning silicon to iron in our typical 20 solar mass star only take about 2.02 years, which is about a week. So some of these things towards the end can get very fast. But there's also this other thing that we see, this tremendous acceleration of the time scale. So this first change in the factor 10 in time scale comes from because the nuclear energy that is being released from hydrogen burning is about 10 times more than from helium burning. But what happens here is that carbon burning actually releases about the same amount of energy per unit mass than helium burning, but it goes about 1,000 times faster. Anybody know why? Any of the students? Oh, the senior people, yeah. So the reason is that the star makes a transition. It gets so hot in the center that it can produce neutrinos. It makes electron-positron pairs that can annihilate as one of the possible processes that makes neutrinos. And the neutrinos don't have to diffuse all the way to the surface, but they can escape from the center of the star when they're being made. And so the star cools very efficiently, and then all this energy is carried away. So starting at that point, the star is not really anymore a photon star. It actually becomes a neutrino star because it's 1,000 times brighter or 1,000,000 times brighter towards the end of neutrinos than it is in visible light. So this gives you this acceleration here. For 200 solar mass, actually something different happens. Again, we have this acceleration time scale. But then somewhat after carbon burning, it gets actually really, really fast. And the reason what happens there is that we have some instantly the equation of state, and the star dynamically collapses. It actually collapses so fast as all of these burning stages here explosively, and this nuclear burning would release so much energy that instead of collapsing to a neutron star or black hole, the star will actually explode and give you a bright supernova, a very energetic supernova. Because it releases all of this energy at once. It's kind of similar to the type 1A supernova. In the can't accept that there's 100 times more mass, and so we also can get out 100 times more energy. So we can get some very powerful explosions out of these big stars. Okay. Now I was supposed to switch to the next slide. One thing that we're interested in is what happens directly after that in this last phase when we reach near silicon burning. Does this here work? Okay. This is a nice movie that then recently done with my colleague Bernhard Müller, where we see the last evolution phase, the last 6 minutes of the evolution in the center of the star. You know, there's the iron core, this is the oxygen burning shell, and just towards the end of the core starts contracting, and the convection gets increasingly more violent. And this is actually very important because it sets some seed instabilities that make the supernova able to explode. So this is what we are currently looking at, and okay, there was okay. So the next thing is, okay, now we have the star start collapsing, and then the next thing that happens is that we have an explosion. And so this is my simple version of this, but we have also some more sophisticated version, again, simulation that Müller has done, where we put this previous model in our simulation, and then you can see how the explosion starts from the central object, and then it will move out towards the star, eventually reaches the surface, where we can see a few hours to days later, when the shock reaches the surface, we can start observing a supernova coming out. What is interesting for my purpose is what happens is that during this explosion, in terms of nucleosynthesis, because we want to use that for diagnostics later. So we have, in principle, we have these burning phases that went from light elements to heavy elements, and now making these shells in the center. And now we have the inner part collapsing, and now we have a shock moving from the inside out. And we have now sort of a reverse of the same type of burning process. First, in the inner part, silicon, oxygen, near magnesium, and it can make a whole variety of different kinds of nucleosynthesis patterns that are characteristic for the kind of explosion that we have. And all of this happens on very short time scales, just a few seconds, and about 10 to 100 seconds after the supernova started in the very center, all of the nucleosynthesis is essentially over, and the stuff is just being blown out. So the first time after the supernova, the star spent maybe 10 million years getting there, and then it does the other half of the important nucleosynthesis happens in just 10 seconds. So it's really a very big variety in scales that play a role. And somehow my switching here doesn't like me. Okay. So this is some overview slide, a very busy slide, how we imagine for zero metallicity stars, how we relate as a function of initial mass, what would come out, what would be the fate of the stars. And we'll give you a very brief guide into that slide. So the very lowest masses, so this here shows the initial mass of the star, and this here shows final masses of what comes out. So if initial equal final, we have just this line through here. So if everything would come out, then you would have just a degree. So at the lowest masses, we make white dwarfs, up to maybe 8 solar masses. Below at low masses, we have oxygen white dwarfs, new oxygen white dwarfs, and above about 8 solar masses, we start making neutron stars, and then the outer layers are being ejected. Everything above this red line goes out, and everything below the red line becomes the remnant of your explosion. And then somewhere around maybe 20 solar masses or 18, there's a little bit, it's not very well known. It's actually not a very rich limit either. There may be some stars below, above that explode or don't explode. We start making black holes. So initially, we would expect that you have your supernova engine in the center, and it has a certain finite amount of energy that allows you to explode the star. But the star gets bigger and bigger, and so its binding energy gets larger and larger. And eventually, you reach a point where the explosion can no longer really push everything to infinity. And then you start an explosion, you start moving things outward, but you don't have enough energy to really move to infinity, and there's also momentum transfer, and things then instead turn around and fall back, onto the central object. Okay, and then maybe at even larger masses, the central object is so big that it can directly collapse the black hole, and you get a lot of stuff coming in. And somewhere above around maybe 150 solar masses, you have this regime that I explained to you before, where we have these big stars that can directly explode from thermonuclear explosions, and you have complete disruption of the stars, and you also have no remnant. You just get a huge thermonuclear explosion, but it works only in a limited regime. At too high masses, this mechanism does no longer work, and instead the thing will continue again, collapsing to a black hole. The other thing that's very important about this plot is the green parts here is where metals, so material heavier than hydrogen and helium, is being made and being ejected, because this is the stuff that we can later see and can use as a diagnostics of the supernova if it's being kept until the present day. Okay, so we have this entire wealth of things that can happen for our stars, but we don't need, to some extent, there's still lots of things that we need to know, and our model is maybe still somewhat like a cow, not quite a spherical cow, but it's kind of a bland cow. And this is a picture that I took in Holland a few weeks ago, where they're standing around. But what we want to know about is how this is just a single cow, for example, or if there's other things. What are the properties of this cow? Right now we have a very kind of prototype thing, a picture of a cow. And maybe it could be, for example, 2 cows, binary cows, or maybe it's 3 cows that form in your halo of 3 stars. And then the other question is, what are these properties, for example, in terms of stars? You would think about do these stars rotate, or we have magnetic fields, so what are special properties? So we could maybe paint a picture on these cows if you learn more about what these stars look like. So maybe in a more simple way, what we want to know is what is the size of the stars, are there binary stars that go around each other, what's the ratio of these stars, what is the distance, are they close or far, is there stellar winds, or is it multiple objects, or are the stars just rotating? So these are questions that we hope to be able to answer at some point to learn about the properties of this first generation of stars. Okay, so in order to do this, what I study is the nucleosynthesis in these stars. When these stars evolve in the burning phases and when they explode, what kind of elements do they synthesize? And do they not only synthesize, but what do they actually eject? Because we know the inner part will collapse to a neutron star or black hole. So this is 2 things that play a role. Actually, there's 3 ingredients. The first thing is the hydrostatic evolution, and then the explosion of the nucleosynthesis, and the supernova. Then we have to look at when the supernova happens, what kind of hydrodynamic instabilities would we have during the supernova, and finally, because if you're not able to push everything to infinity, what of the material is actually coming out, and which is what is falling back onto our landing. So what I did is we made some kind of huge library of nucleosynthesis. So this shows you as a function of initial mass of the star, here the elemental mass fraction, some color coding is the how much of these metals or of different kinds it would make. So this is this here must be neon and so forth. So all of these metals, we can make some huge library of all of this that we can use to study. Then the next thing is looking when the supernova explodes, what really does happen. And it turns out it makes a big difference whether the star was one of these primordial stars or it is a star that forms today. So here I show you square brackets metallicity 0, so the solar metallicity stars, and this is what happens for primordial stars. And you can probably see there's structurally there's quite some difference in the amount of mixing. There's much more mixing in solar metallicity stars than you would see in these primordial stars. So here you see the helium, but you see also deeper in for the metals like silicon. And the second thing is that also happens is the amount of fallback that we get from these stars. This shows you here again population 3 star in blue, so the first generation of star, and the population 1 star, so modern star down here. And again, what we find is that these things are actually quite different. And for the population 3 star, we get a lot more fallback than we get for our population 1 star. And both for the mixing that you see that was very different, as well as for the amount of fallback that is very population-free stars tend to be much more compact. So modern stars, they may typically end up with fairly expanded envelopes by the time they die, whereas population-free stars, they stay very compact and very hot objects, and that changes both the amount of mixing that we have, and because they're more compact, also how much material does make it to infinity, but is instead falling back. Okay, so the pictures, unfortunately this didn't come out. Well, I have to put up the luminosity a little bit in order to show you the dark moons of the first star. So we get in principle some pre-supernova structure. Unfortunately, you can't see this now very well. When we have some abundances before the explosion, then we will have the nucleosynthesis in the explosion itself, and you can see there's some modification in the abundance pattern as the supernova shock runs through this. And then finally, there will be this mixing. The mixing happening, and then this smears out the abundances, and then we have to, at some point, which you can't see, that some inner part will be falling back onto the star, whereas only the outer part is being ejected in a very picture. Okay, so what do we do with this? And this is where stellar forensics comes in. So we have, in principle, stars that make nuclei. And our picture is that we have this very first generation of stars, and it ejects all of these little nuclei, and then whatever came out is being incorporated in the next generation of star that are sort of polluted by this, where this first generation of star leaves their fingerprint on them. And then we have our smart observer that looks at these fingerprints of abundance patterns on these stars that we can see today. So there's some stars that are around about 0.8 solar masses. They have long enough lifetimes that they live as long as the age of the universe. And they are now just about to reach the end of their lifetimes, when they start getting a lot brighter, so we can see them out in the halo of our galaxy and measure the abundance patterns on them reasonably well. So the basic idea is, again, we have this first generation of stars. It makes some specific abundance pattern. We use some large telescopes to observe these stars. Then we compare that with the abundance pattern that we predict from the models, and then we can, for each of these stars, we can try to estimate what was, for example, the congenital mass of these stars. And then the ultimate hope is to try to reconstruct what is the initial mass function of the first generation of stars. So this is the agenda, and maybe we'll switch for me. Okay. So for this is one example where we have the Caffau Star. This is the most metal star that we know, and we were trying to make a probability distribution of what kind of masses would fit best for that star. And in this case, we found a very low mass, and there was a very reasonably good fit for the Caffau Star in terms of overall abundance pattern. Another star that is very interesting is this star SMSS J01, J031, and so forth. We typically just call it the Caffau Star these days. So this is the star with the least least amount of iron in the spectrum that we know today. So this is, for example, here's a star at metallicity of minus 4.1, where you can see some lines in the spectrum. And if you go to HE107, the metallicity of minus 5.3, we also call it the crystalline star, it's not this here, so it's this star. And then you still see some iron lines in it, but now for that star, the Caffau Star, when you look at the spectrum, there's really just nothing there. And if you try to match something there, you can roughly estimate an upper limit of what would be there, so that you would not have missed it. And at the time, so this shows you different abundances of minus 5.7, minus 7.2, and minus 6.9 for its estimates for where the line would be if it was present. And so at the time, we derived some kind of upper limit for the iron abundance of around minus 7.1. So what's the iron? It should be somewhere here. This must be the iron part. Okay. So another thing that was very remarkable about the star, so really there's essentially very little is there. There's almost nothing has been measured in the star. We have upper limits for many elements, but only a few things have been measured. Carbon, magnesium, stress, and also iron has this very strict upper limit. And it turned out that for this specific star, the calcium that he observed there could actually well explain from hydrostatic hydrogen burning, because the hydrogen burning in this first generation of stars is extremely hot. Whereas in almost all other stars that we observe, most of the calcium comes from the explosive nucleosynthesis. But in this case, because there's so little iron, almost all of these heavy things have to fall into the star. So what is left behind, what is ejected, the calcium must actually come not from the explosive nucleosynthesis, from some early hydrostatic burning phases. And I had actually seen this in some simulations maybe 10 or 15 years ago, when at the time before this is so little calcium, nobody's going to ever be able to observe this. But this gives you a very good idea how remarkable the telescopes and observations are nowadays based on. You can see such tiny traces of material in the stars. So in the meanwhile, there has been another update, and we have been able to constrain the abundances even more. There's a new measurement of oxygen is now also present in the star, and the upper limit of iron is now down to minus 7.5. So minus 7.5, this means there's about 30 million times less iron in the star than in the sun, per unit gram. So that's really very, very iron-clean object. And it still is just an upper limit. It may very well be that there's essentially nothing there. But it's just from the amount of telescope time of the spectrum it can take, how deep down we can go. Another thing that we were trying to work on, this is what I showed you a little bit earlier, is reconstruction of the initial mass function. So what we have looked at is different data sets. Was one extended data set from Barton, or also Carrel. They have put together a data set of different low metallicity stars, and then now you can take this entire set of different metallicities of stars, and for each of these sets you find a distribution of possibly best matches of what are the progenitors of these stars, and then you combine all of this together according to how good these fit actually were, and then try from that to reconstruct what the initial mass function of the first generation of stars should have looked like based on the abundance pattern. And what we found with these two sets is in both cases something that went down here and had a second hump here and then went down. So it's overall not inconsistent with some kind of salpinta and with this steep drop here, except there's this little dip here, and initially we were wondering, okay, could this be there's a really primordial in the initial mass function, because this is very suggestive. But we now continue starting to wonder whether there isn't something else that happens here, that stars in this regime don't match very well because they don't actually explode the supernovae, but you may see something that stars somewhere around here collapse as black holes, and then you have another window of possible explodability of stars around 25 solar masses or so, and then things are less likely to explode again as supernovae. So it might also be a property of stellar structure that gives you this suggested primordial pattern. But the pattern is still representative of what actually might point to the first generation of stars in terms of initial masses, but not what actually formed its initial masses. So this is something that one has to be very careful about. And this is only what the only diagnostics that we actually have. So that's what we're going to be working on. Has also been I can show you some other work that we have done on actually simulating binary stars in simulations. So this shows you, for example, the ionizing flux output that comes from single and binary stars. Unfortunately, the colors are not very good, so we have these stars of different masses that correspond to these colors here, and they have different lifetimes, and this gives you the ionizing flux. In different bands, the Loiner band, this is for dissociation of molecular hydrogen into helium hydrogen, or hydrogen ionization, helium ionization, and setting ionization of helium. And when you look at now a combination of binary stars, so here's just a single 68 solar mass star, and the question is that we wanted to answer is, okay, let's assume we have a cloud that makes stars in the center, a primordial cloud, and the scenarios is we can either make single 60 solar mass star, or maybe the star has fragmented into two stars. And it could have been, for example, two 30 solar mass stars, or maybe it's two stars that have mass ratio of 1 to 3, and 45 solar mass star, and 15 solar mass star. And we want to see what's the difference, what does the fragmentation of the star actually change in the outcomes. And once you get the overlay of the ionizing fluxes of the two stars that come out here, then also the ionization that you find in the vicinity of the star becomes somewhat different. So the weakest ionization you get for the 230 solar mass star, for the 45 and 15 solar mass, you get a slightly larger region, and for the 60 solar mass star, it puts out somewhat more ionizing photons on a short time scale. You get much larger fraction of ionization in the vicinity. And the other thing that we were interested in is the enrichment that comes from these binary stars. So you also find out that these stars explode the amount of how the metals are being distributed in the two 30 solar mass stars, depending on whether they get core-column supernovae or hypernovae. So again, it depends a little bit on what the explosion of these stars actually is, how the metals are distributed. But typically, for a powerful explosion of 60 solar mass star, you are able to get the largest enrichment on the largest scale, because also we have ionized larger region where the supernova explosion can run into a region of low density and distribute the metals further out. Okay, do we still have 2 minutes? Or is it?
2 minutes.
Okay. So the other interesting things, because I showed you at the beginning my appearance of the supernovae, what happens with these things, and because it's very, very interesting. Okay, is it just these normal stars that I showed you so far, so the big stars? This shows you roughly as a function of initial mass from 140 to 260 solar masses, what we expect to come out of these bulk elements. And the other thing that shows you here is the explosion energy in beta, for beta stands to 10 to 50 watt, which is the typical explosion energy of a normal supernovae. And so this here is like 20 times the explosion energy of a normal supernovae. And if you go here from the lower end where the explosion energy can be sort of color, you can't actually see the explosion energy curve of the sun ion, but somewhere runs around here where the label for the explosion energy is still visible. So it runs somewhere around here. We start with 2 times the explosion energy of a normal supernovae up to about 100 times the explosion energy of a normal supernovae. At the same time, the other very interesting curve is that of nickel 56, which goes essentially nothing to almost 50 solar mass of nickel 56 that come out. And so what does these numbers actually mean? You all know about the type 1a supernova that we used as a standard camera to measure out or discover the expansion of the universe. And there it's about 1 solar mass and makes about half a solar mass of nickel 56. And it has the explosion energy of about 1 meter. And so these things here make 50 solar mass of nickel and have 100 meter explosion energy, so it's corresponds to 100 type 1a supernova going off in one spot. So this is how impressive these explosions really are. Unfortunately, not 100 times as bright because you have 100 times more mass, and so the photons can't get out. Everything expands, and by the time it becomes transparent, all the radiation gas has PDD work, and we don't see it. But it's still can be a few times brighter. The other interesting thing is the abundance pattern that these kind of stars make, and this is what I show you here. It's a function of the charge number of the elements. I show you the production factor relative to solar. So the solar abundance pattern has already some kind of odd-even effect. And this is already divided out here, and this is what the yields are relative to the solar abundance pattern. So you see silicon, for example, relative to phosphorus, 100 times overproduced relative to the solar abundance pattern. And the big problem is that we haven't actually observed any star that shows this abundance pattern. So there's a big problem today that we haven't observed any of these abundance patterns that we can very clearly predict. And the other problem is that experience in the supernovae actually fully understand how the explosion works, whereas for normal supernovae it's a little bit less clear. So this is the only case of supernovae that we actually know how the explosion works, and it works well. And yet it makes predictions that we never see. Okay. We go to this slide. Okay. So as a summary, the initial mass function of the first generation of stars is still somewhat elusive, and we are just collecting evidence, and I hope that at some point we can use nucleosynthesis to better effect of the supernova that contributed to it. So for some of the stars, the abundance pattern seems to be suggestive. This is probably the strongest word I can actually use. There may have been possibly binary stars, stellar forensics. So determining abundance patterns of what the first stars left behind is probably still the best thing we can do to learn about the IMF at the present, but maybe in the future it will change. And the problem, of course, with the parents with nucleosynthesis ashes we haven't seen so far. Thank you.
The podium is open for questions, and as usual, we start with the students and postdocs. You're a senior postdoc. Students? So, David, go ahead.
So, Alex, actually, are you familiar with this new Aoki result where he claims to have seen the nucleosynthetic, the odd-even effect in one of these metal core stars? So there is actually a candidate now for the odd-even effect. The other thing too is there are 3 observational candidates based on light curve structures for parent stability supernova.
Yes. But not for the first star. So this where they say this, they possibly see some odd-even effect in there. When we look at this, it's still way better matched with lower metallicity, with lower mass stars than with parent stability.
So the other issue too is the issue of bias, where parent stability supernova will enrich local gas to metallicities well above those surveyed in the metal core stars surveys to date. So it's intriguing but not dire.
Yes, but it also about the stars that we use the diagnostics, but we can be reasonably sure that this enrichment only from one supernovae. In those we haven't never seen this pattern, and so maybe they enrich more material, but there could also be other contributions that come in before you form the next generation of star.
Next question, what here?
Probably I missed it, but what about the environment of the metal core stars?
So, sorry, I didn't catch
What
that.
about the environment of the metal core stars?
Be implied?
Yeah, what's the situation on which position of the galaxy they are in the dense gas region? Or
Well, we find them mostly in the halo. Because there, I think the field is not so crowded, you can observe them, and not that we notice much better than that, but most of them we find in the halo of the galaxy, where generally this is somewhat older and has many of the metal core stars. There might still be, most of the metal core stars may end up in the bulge of the galaxy, but there will be much harder to see because there's so many more stars that are not metal core.
I presume that different elements are ejected with different speeds, I guess, depending on where they were located in what shell.
Yes.
So how much of a difference do you expect or are you estimating in the ejection speeds, and how much does that affect the further mixing with the ISM to build up the next generation of stars? So do you really expect that you form a second generation star that has exactly the same composition as the ejected material?
Well, there's many effects that can play a role. Some have this dust formation that can carry away some of the metals, but yeah, this picture that I showed today, we were very naive and simply assumed that everything comes out as homogeneized before you form the next generation of stars, because when you allow for this mixing, it opens up an entirely new field, and yes, you can then make, of course, lots more things if you open up the parameter space. There's many more possibilities. Yeah, things initially come out with different speeds, so they for the most part. Some of them may move somewhat slower, but sometimes there might also be bullets of material from the iron core that come out faster because of great Heller instantly forming during the explosion. So yes, if this thing is not well homogenized before you form the next generation of star, or there's large variations from direction to direction and things as well, then you could get different results as well.
Next question from Matthias.
Yeah, we have two questions. First is, what makes primordial gas clouds fragment on very small scales? And the second is, how reliably mixing processes modeled in your simulation?
I'm not an expert on this first star formation, but I think it's mostly the cooling that plays a role that allows you to do the fragmentation to start forming.
That's exactly what cooling is, because I'm wondering what is cooling.
What's cooling? Well, it's emission of photons from molecules. now as well.
So
He's the expert.
cooling is often, or most cooling is provided by the H2 molecule. The temperatures are hot so that the lines are emitted, that the molecule has intrinsically. There is also at very high densities collision-induced emission. So what happens is at densities of 10 to the 11 particles, as the particle cruises by, as another particle cruises by a hydrogen atom, there is a temporary dipole induced, and this is enough to give rise to very efficient cooling. Then you can also have HD cooling, which despite its low abundance can contribute in certain environments to the dipole cooling power. The way you form it, there are two chains here, O- and O+, where you can form the molecule in the gas phase.
H minus and H2 plus. H minus and H2
What
plus.
did I say?
O
sorry,
minus.
yes, H2 plus. And there's also the three-body H2 formation at very high densities. But I personally believe that the fragmentation, to come to your first question, takes place in the disk. Because the accretion disk around the first star usually gets a mass load onto the disk that exceeds its capabilities to transport the material inwards by viscous or gravito-viscous transport processes. So it has no chains but become too unstable, then it fragments first into binary, then into multiple stars. That is, I would say, the pathway to get A low mass stars and B not only binaries but many.
I'm not sure this is the only pattern. The picture that I showed on my work seemed to be fragmentation. It was not really a disk. So there's probably this multiple paths that make it.
If it was in a disk-like structure, these things would have been big and they so they have not calculated. So Norbert, and then on this side.
Is it understood what the physical reason is for these pair stability supernova producing the odd-even pattern?
Yes, because we don't have enough, well, we have no initial metals, and so this first of all allows you not to get, typically all of these elements that have odd Z's have a neutron excess with them. So you have to make a process to make the extra neutrons. Typically you can get this neutron excess if you have initial CNO abundances, but you don't have that in top 3 stars. In the second phase you can do this during hydrostatic carbon burning, but in the appearance of the supernovae, this phase is very brief because you have explosive burning, so it collapses and there's very little carbon being made, and it's not convective, and so you just don't generate this neutron excess during the burning phases. So, Len?
At what redshift could we observe these stars? I mean, how bright are they? Would James Webb be able to observe them? That's dedicated to the first stars.
I think it will still be challenging to do this because you still have the atomic hydrogen around it, and so you would only, the first stars themselves, I mean, they're too faint, they're too far away, so the only thing that you might be able to see is the supernovae from them. There you might have some chance, but they, typical supernovae, you get the temperatures is not so high, so around 6,000 Kelvin, and you would only get the higher energy, only at some point the energy can escape, and then you have everything being redshifted, so you can see them only in the far infrared. And I think James Webb doesn't go quite out. If you have a star at a redshift of 20, it doesn't go quite out to see the peak of the supernova light curves. So it will be still some faint object. If they're somewhat closer to us, maybe redshifts 10 or few, then you would be able to see them. The other option is if they make gamma ray bursts, those we might be able to see. I think the supernova are somewhat harder, but that has a different perspective on it. I think it will be difficult. There will be a limit.
Pairing stability supernova will be visible at redshift 30 with JWST, and then the core collapse events 10 to 15.
But you have to only on a very optimistic assumptions.
No, JWST will clearly see them, but it has to be looking at the right place.
Another problem is that these things only last a month in their rest frame with redshift 30. They would now last for 30 months, and so you have to be very patient to see actually a transient source coming up and coming back down. disadvantages of doing observing supernovae in high redshifts.
I have two different questions. In some of your very analytical stars, boron is almost as abundant as carbon. In fact, boron, almost as abundant as carbon. Is this understood?
No, what the plot showed is, that was probably misleading. It showed the abundance relative to solar, so it was the...
Well, nevertheless, you see, the ratio of boron to in the solar system, boron is much better than carbon. In your star, it was almost illegal. This is understood.
No, it's the abundance is relative to solar. It has the solar abundance. If they have the same level, it has the solar ratio of boron to carbon. Not the same abundance.
Yeah, but the radius was down to almost a magnitude.
Yes, so the boron you can make in part by spallation from neutrinos in the supernova explosion. And so it's a primordial process. So you make carbon and then high energetic neutrinos hit this in the moon. It's being destroyed too easily in the explosion. The boron survived, but the beryllium was not made.
Okay, my other question is completely different.
The boron is closer.
You showed a number of pictures and movies with this nice movement during forest formation and experiment. And this turbulence must very much depend on the initial conditions which you had to assume. If you were to assume spherical symmetry, you would get very boring pictures.
Yeah.
How typical will these pictures be? Because if you make different assumptions about the starting conditions, the picture would, well, look different. So in a way, these pictures, in my opinion, are very meaningful if you can make averages in some of the large number of examples.
Yeah, this is what people are working on. They look at different tables.
How many explosions of the same type, which differ just by turbulence, are you really able to do?
I showed one of the simulations where they, for the formation part, where happened maybe dozens of stars forming where they had this spectrum of different masses for the supernova later. Depends on what kind of detail you want to do all of this, because even a single one of them can be challenging to do with all the physical detail that we need to do to fully do the mixing from end to end, with everything being resolved and all the cooling being, the chemistry being so this is something that we're still working on to do this properly.
Sounds good.
You showed a couple of cases which you could determine or give an estimate of the progenitor mass of 65 solar masses, 10 solar masses, and so on and so forth. We were wondering about the empirical lack of evidence for the pair instability supernovae, for which you need stars significant around 120 solar masses or above.
Yeah,
would we know from observational evidence, as sketchy as it is, not the most simple conclusion that there are no extremely massive stars, significantly say below 100? Or what is your take on this? Should we throw this idea overboard, that the mass scale is 100? Or
It's below 100. So I mean, they're also very present very, very rare in our present galaxy. So maybe they were not the typical case that we know. And we had just haven't found those few cases where it happened. So that's what we don't know. Or there's some reasons that, as Dan, for example, pointed out, that you always get a much higher enrichment and you're not looking in the right place for this, because these things, for some of these best matches, the match that I showed for the most particular star, for the Caffau Star, there was effectively only ejected 1 or 2 solar masses of metal. There's very little metal in this kind of explosion that would actually make it out, because most of the metals disappear from the center of the black hole. Whereas when you make the pairs in these supernovae, you always get out 100 solar masses of metals. And so you could enrich things at much higher densities. So that's a way out. And usually when you look at those stars that look very special, very peculiar, because they have essentially no metal lines. They stick out. And if those make stars that have a vitality of maybe only -2, so 100 solar, then they might be hot to make drops in our regular algorithm for finding them.
Norbert, are you still wanting a second question?
No, I'm not sure.
Okay, so